Okay, so today we're going to start a lesson that's kind of near and dear to my heart. It's how I started off in aviation officially, is with Rotorcraft. So I'm a former Army helicopter mechanic, and I'm happy to talk all about some helicopters. Now, that's not where my career ended, but it's definitely was the first 6 years of pretty intense maintenance. I always say that I became a real aircraft mechanic on the flight line in Baghdad. Before then, I just kind of like knew facts and stuff, but that's really where I kind of came into my own. So to get us started with Rotorcraft, we're just going to talk about some basic aerodynamics. How does a helicopter work? How is it supposed to work? And so if we can understand, how it generates lift, how it moves from side to side, backwards, forward, and all that good stuff, that will help set the stage for learning all the other little parts and pieces. Now, don't let Rotorcraft scare you. They're really not too terribly different than everything else. They all have the same sort of avionics per se. They have the same engines. They just get applied a little bit differently. Where they really start to differentiate is with the transmission and up into the rotor system, and then how they work. That might look like total magic, but in all reality, once you kind of understand it, you're like, oh, I get it, and it'll all kind of come to you. And ultimately, if you ever have a question, the maintenance manual is always there. So let's start talking about some Rotorcraft aerodynamics. Helicopters may seem really complicated and kind of a mystery, the fact that they can just hover and float in air. But once you kind of start to understand the aerodynamics that come with a helicopter, it really isn't just too terribly different than an airplane. It's just the way that they go about creating the same effect allows them some flexibility in how they apply it. So first off, let's just start talking about the forces that act on a helicopter. So that way we can kind of understand what's the environment the helicopter has to exist in. All right, so in a no-wind condition where the helicopter is just simply hovering and it's just parallel to the ground, this is how the four fundamental forces, drag, weight, lift, and thrust, are equalized. So first off, gravity is going to pull the helicopter to the ground, it's going to hold it on the ground, and that is weight, all right? And if it's not doing any kind of forward or sidewards flight, drag also wants to weigh it down and pull it to the ground. Simultaneously, the rotor blades, because of Bernoulli's lift, as the blade swings around, produces a upward thrust. It actually produces lift that causes the helicopter to raise into the air. Now, as the helicopter transitions to different phases of flight, these vectors are going to correspondingly change as it goes. If lift exceeds weight, the helicopter will climb, will extend up into the air. If lift is less than weight, the helicopter will sink, it'll descend back to the ground. And if thrust exceeds drag, the helicopter will go faster and faster. And if thrust is less than drag, it starts to slow down. Now, one of the things that make a helicopter unique is that it can do sidewards flight, and it can also fly backwards. A matter of fact, a lot of times whenever they go to take off, they'll pitch up and then they'll back up from wherever they were at because they were close to something whenever they landed. So you'll see this pretty often. Now, what makes it possible is simply with an airplane, you have thrust is basically always going in one direction. The engine and the propeller is fixed, and then that causes the lift to happen in relative to the wings. Well, with a helicopter, because you have a helicopter that's spinning like this, as that prop pitches one way or the other, the reaction of the aircraft follows suit. So if you wanted to pitch forward and you wanted to fly forward, you would pitch the prop forward or the rotor forward, and it would result in forward flight. If you wanted to go backwards, you would pull back on the cyclic, causing the rotor disc to pitch backwards, and you would fly backwards. Same thing from side to side. And that is how a helicopter is able to be so maneuverable and move around, is that you've effectively taken the prop that's on the front of an airplane, set it on top of the whole apparatus, and then allowed it to pitch any one direction it wants to go. Now, there's some challenges that come to that, like with retreating blade stall, but we'll get into that here in a minute. But know that that's fundamentally what allows a helicopter to be a helicopter. Now, another force that you have to think about with helicopters is the anti-torque force. So if I'm hovering and I'm flying, just sitting there at a hover, that rotor blade is spinning this way. that means that naturally, just because of action reaction, I actually want to turn that way. Now, if you notice that in helicopter crashes, if they lose their tail rotor, immediately the whole fuselage will want to spin like that. And the reason being is that tail rotor is not really a tail rotor, it's a anti-torque rotor, meaning that if the helicopter blade is going this way, the anti-torque rotor is going to push a massive air out to help keep me stabilized. Now, the way that the helicopter controls its yaw is by feathering and unfeathering that tail rotor. If they want to turn one way, they might take a little bit greater bite on the tail rotor to cause it to overpower the main rotor and spin the nose one direction. If they wanted to turn the other way, they'll flatten the tail rotor blades out and let the main rotor take a bigger bite, and it'll turn that way. If it wants to stay straight, it'll be rigged so that way the tail rotor naturally wants to sit in a certain position to allow that straight and level, or that straight orientation. Now, that is how a yaw, or that's how the helicopter actually controls its yaw, is through the anti-torque rotor in the back. And torque is one of the biggest forces that comes to bear on the helicopter, more so than any other aircraft that's out there. All of them have to contend with P factor and right turning tendencies and all this other kind of stuff, but it's nothing compared to the amount of torque that main rotor is that's putting on the airframe of a helicopter. Now, the classic tail rotor could have multiple blades, and it's always going to be situated on one of the two sides of the tail boom, just like this. But there's other types of tail rotors that are out there. Okay, common tail rotor configuration is called the fenestron tail rotor. Essentially, this is kind of like similar to a ducted fan. It's a tail rotor that's been enclosed so that the blades aren't just spinning all willy-nilly out in the open. Now, the advantage of this is it's safer to work around because it's really difficult to like walk into it. Now, you guess you can still stick your hand in there or maybe your head in there, but one of the key things with the classic tail rotor design is a lot of people want to walk into that, and you'll see people get killed. So you'll see these be popular in EMS and emergency helicopters, like this one's on the back of a sheriff helicopter that I'm sure is probably being used for medevac. You'll also see it real popular if it's going to be operating off of ships, because ships get off kilter and people have a higher chance of walking into one, and the fenestron helps that out. Now, there's downsides to them as well. They're heavier, they don't have as much tail rotor authority. They work, but they don't work as well, and so you'll see a lot of people get all up in their feelings about the fenestron tail rotor, but they have their place just like anything else. All right, another one that's also fairly common, used to not be so, but now they definitely are becoming more and more commonplace, is the NOTAR, which basically is a shorthand version of saying no tail rotor. What this does is it takes the same sort of force that would turn a tail rotor drive shaft, and it turns a ducted fan. It pulls air into the tail boom, pushes air down the tail boom, and then out a vent on the back left-hand side of the tail boom. Now, there's little vents that open and close to allow for more or less air to escape from the tail boom. This, in turn, causes the tail rotor to swing one way or the other based on how much air is being pushed out the fan. But that's a NOTAR tail rotor. Now, another force that acts on a helicopter that's kind of unique to a helicopter as an assembly, it's not necessarily unique to just helicopters, is gyroscopic precession. Now, airplanes experience the effect of gyroscopic precession on their takeoff and landing whenever they're in certain configurations. They also will experience gyroscopic precession inside the instruments where there are gyroscopes. But helicopters are unique in the fact that it is effectively one large gyroscope. And then whenever you have one large gyroscope that's going through the air, gyroscopic precession becomes a lot more relevant to what you're doing. As the helicopter rotor spins, you input a control input. At a certain point, you'll get the max deflection of the rotor 90 degrees in the direction of rotation from where that was attached. So if I go here at the 180 degree mark, I get max deflection at 270. So try this again and keep it straight. So I push up right here. Notice that even though I'm pushing up in line, but you're seeing the deflection off to to your right, my left. That's because of gyroscopic precession. Now, this becomes extremely relevant whenever we start talking about controls, because imagine if you have a rotor disc that's spinning like this, and you say, hey, look, I want to go forward, and so you press forward, and so the control, like pushes up on the back and pulls down on the front to make the rotor disc do like this, or so you think, and it actually does like that, and you go off to the other side, or I guess it would go this way. That's how gyroscopic precession impacts the controls of a helicopter. Now, the way they get around that is that they say this is where the control is whenever it's center line and it's going to go forward, right? Then what you effectively do is you calculate 90 degrees of control input from the yoke all the way up to the top. Now, you as a mechanic just need to understand what's happening, because you're going to follow the rigging instructions in the manual, and you'll rig it per the manual, and the engineers have already thought through like where they're going to get like every degree of that 90 degree all the way through the control system. And you'll even see up in the if you look at the swash plate and the flight controls of different helicopters, you'll see these weird angles because they've effectively gone in and they've accounted for that 90 degrees in a different way. And so you'll see like different like little angles inside the way where the pitch change link's attached to the bottom of the swash plate, or the top of the swash plate and to the bottom of the hub, or maybe a certain control arm somewhere down in the chain of flight controls will be just a little bit off, and you'll think that's really odd. Well, the reason being is that all of those add up to being 90 degrees, so that way whenever you actually go forward, you're actually putting up a left side control input, so that way you get max deflection on the forward side. All right, another tendency of helicopters is kind of unique is drift. And this is something you don't ever see with airplanes, because they're just not built in a way that you'll actually have this. But essentially, if the helicopter is set up hovering with no wind and it's just left to its own devices, it's going to naturally want to drift in a certain direction. So there's several ways that the aircraft designers have set up to kind of compensate for this. One is the transmission can be mounted at a slight angle. So like on the OH-58, if you go and look on the left-hand side, it's slightly lower than it is on the right-hand side. That's so that way whenever the helicopter's at a hover, it'll squish down and will level out, and it'll help cut down on that drift fairly significantly. Flight controls can also be rigged so that the rotor disc is tilted to the right slightly when the cyclic is centered. So you'll definitely see that if you're looking at a hovering helicopter, it'll always look like it's canted one way, and that's part of the reason why. If the transmission is mounted so that the rotor shaft is vertical with respect to the fuselage, the helicopter hangs left skid low in the hover, and the opposite is true for the rotor system turning clockwise when viewed from above. So meaning that like the designers set it up so that way one side of the helicopter will naturally kind of just like be lower than the other one, and that'll keep it from sliding off, in one direction or the other. And then in forward flight, the tail rotor continues to push the right, and the helicopter makes a small angle with the wind when the rotors are level and the slip ball is in the middle. This is called inherent side slip, meaning that it kind of naturally wants to fly a little bit sideways, and that's all to help compensate for drift. Now, just like an airplane, helicopters have to contend with ground effect. Effectively, what the ground does to the downwash of a helicopter is causes a level of friction that puts pressure on the wingtip vortices that come off the tip of those rotor blades. Now, as those vortices get tighter and tighter and tighter, it actually allows the rotor to become more effective, and it feels like you're kind of hovering on this little cushion of air, and the helicopter becomes more effective. Now, once you get up above a one rotor width of the ground, those vortices start to open back up. As they open back up, you lose that little extra bump in lift, and the helicopter has to work harder to maintain its climb. You can feel the same thing in an airplane. You come in at a ground effect, it'll feel like all of a sudden the plane wants to climb right as you're about to touch down on the ground, and it feels like you're sitting on a cushion of air that you have to fight through to maintain the right profile to land. The same thing happens with the helicopter. Same dynamic, but it's a lot more prevalent because in a helicopter you spend a lot more time close to the ground and a lot more time hovering around in ground effect. Now, forward flight looks like this. Once the forces have been balanced, you're going to tip the helicopter forward just a little bit, and that's going to allow that thrust to start pushing off on the ground, and off you go. And the resultant vector between the thrust and lift is just simply forward movement. Now, if you were to imagine flying forward at 1 to 5 knots, you've got the front half of the rotor system is still creating a vortices, causing the helicopter to push up. But what you'll notice is on the back half of the rotor system, there's actual air being pulled from the top of the helicopter and pushed down, causing it to push forward. Now, as the helicopter begins to pick up some airspeed, there's a couple of things I want to point out. Notice that the blades begin to kind of curve up or start to gain a little bit more of an aggressive pitch. That's called coning. You'll see this whenever a helicopter comes to land as well. But like you'll see that as the blades come under load, they begin to curve up in a pattern we like to call coning. Also, notice that as the helicopter gets more and more forward momentum, more and more of the downwash becomes pushed underneath. Even the top of the forward vortice, it starts to wash underneath the helicopter, creating a forward flight pattern. Now, something else that's kind of fundamentally unique, and one of the big holdups on helicopter performance is called a dissymmetry of lift. A dissymmetry of lift, resulting what's known as retreating blade stall. Now, imagine if you were looking up from the top down on helicopter blades that were spinning, and the helicopter is going this way. As you encounter, like you're going 100 miles an hour, so it's 100 miles an hour relative airspeed coming down into the helicopter as it's spinning around. But this blade is having to spin at 100 miles an hour itself. So what's the resultant speed of the ascending blade? It means the blade that's coming around, making a rotation. Well, it's 200 miles an hour relative speed, because you have 100 miles an hour that it's traveling, plus the blade is having to spin 100 miles an hour. You add those together, it becomes a 200 mile an hour blade. Now, simultaneously, what's happening on the other side? If it's going 100 miles an hour this way, and it's spinning away from that 100 miles an hour, well, the resultant speed is 0. So now you have this situation where this side is going 200 miles an hour, and this side is going 0 miles an hour. The result of that gives you a couple of things that happen. One, the faster the helicopter blades spin to get the helicopter to go faster, the closer you get to this helicopter blade over here, breaking the sound barrier, hitting compression waves and starting to really jostle around and do that kind of number. At the same time, on the flip side of it, as this one's starting to break the sound barrier and really get going fast, this one's going even slower. So if you were to graph it, the distance between them gets greater and greater and greater the faster the head speed of the rotor gets going on. And that causes what's called a hop. It starts doing like this number. It also causes one side of the helicopter to produce more lift and the other side of the helicopter to produce less lift. So that means that it wants to roll like that and lose control. All of these things are all what's known as the dissymmetry of lift, and the condition it causes is retreating blade stall. Now, this is the single thing that has held helicopter performance back for years because it's just kind of a physical reality. It's really, really difficult to make the ascending blade not start to buffet, and to do something with the retreating blade, because the faster the helicopter goes, the worse the problem gets. It's kind of like this chicken and the egg kind of scenario, that we can make the head speed go faster and faster and faster, to where if it was just one side of the rotor disc, produce more and more and more lift so that we can go faster and faster and faster. But the more you do that, the more you start to go the opposite direction on the other side, and you cause more problems. Now, one of the most successful negotiations or navigations of retreating blade stall and pursuit of helicopter performance has been the Chinook. Now, this tandem blade configuration allows for the ascending blade on one side to offset the descending blade on the other side. So that way, on both rotors, you have an ascending blade. The result is much faster ground speeds. The Chinook is the fastest helicopter in the Army's inventory by far. It also allows for a high degree of maneuverability. You wouldn't think it, but because it's so big, you can almost think of helicopters as being opposite of jets. That the smaller jet is more nimble, the bigger jet, it has more body to turn, and so therefore that kind of makes sense to us. Helicopters are an inversion of that. The bigger the helicopter, the more power they have. Generally, the more maneuverable they actually are. Whereas the smaller helicopters are a little bit less maneuverable because they have less power and they're not set up. They're not arranged like the Chinook is. Now, the Chinook can lift a lot of things. It can go really fast. It's a great aircraft by far, but it is probably the most successful showcase of how to beat retreating blade stall. However, it still has its limitations because you still have blades that are losing their lift because they're oriented perpendicular to the or in line with the relative wind. Okay, another example of beating retreating blade stall is the Kamov. Now, the Kamov became very popular over the past couple of years because there's several of them got shot down in Ukraine, and they look so ridiculous because you have two rotor systems stacked on top of each other, and I don't even want to begin to try to figure out how you would end up rigging a system like that. But essentially, it's the same idea as the Chinook. It just instead of having two different rotor systems on pylons separated from each other, you have two rotor systems stacked one on top of each other. So that way, if you pick up, you push up with one blade, you'll affect the other system on top of it. And now the result is that you still have all the advantages of a helicopter, but you also offset the retreating blade stall because as one blade comes around in one direction, the other blade is going around in the other direction, and the vibrational patterns of the two should cancel each other out. The asymmetry in the lift should also cancel each other out, and the result is really good ground speeds, a really stable, strong platform. That being said, the Kamov is almost exclusively used for attack as opposed to actually its lift capabilities, which I always thought was kind of telling. Now, the most modern attempt to overcome these problems with a dual stacked rotor like this is the Sikorsky Raider. Now, don't let the prop on the back make you think that it's a tail rotor because it's not. It's a pusher prop to try to make it go faster. The two blades on top of each other enable helicopter-like operations. However, they also cancel out the retreating blade stall on either side. Now, the problem that the Kamov runs into is that trying to get that extra airspeed from the blades is difficult because of the retreating blade, and also you have all the other dynamics of simply just trying to swing a blade around at an even higher speed. You eventually kind of hit a plateau, kind of the point of diminishing returns with your ascending blade. So they've chosen to attempt to fix this by just simply taking what would otherwise be used for a tail rotor and using it as a pusher prop on the back. So that way, once this helicopter gets up to speed, they can just increase the pitch on the pusher prop on the back, and in theory, it should push it even further. And then the air washing over the top of either blade should cancel out any dissymmetry of lift or anything else like that. And then the descending blade is more or less rendered irrelevant, just kind of like there for drag, and that's about it. It's a pretty ingenious design, but you can already see like there's going to be a lot of moving pieces, a lot of complications to have to deal with, especially in like a battlefield environment where things are inherently chaotic and the supply chain is somewhat unreliable, especially in a large-scale combat operation. So you can see like why it's been kind of hard to get beyond just say the Chinook as kind of like the leading contender for beating retreating blade stall. But there are a lot of people out there working on it, trying to figure out how to improve the helicopter, through that retreating blade stall barrier. Okay, so what happens when a helicopter loses power? Well, it's going to go undergo. It can't like glide to the ground like a normal airplane. It's going to do what's called an auto rotation. So no, the way an auto rotation works is that you're going to be flying around like at forward flight, like you see on the left hand side of this graphic, and then all of a sudden you're going to lose your engine per se. Like something's going to be wrong, and you need to auto rotate to the ground. Well, what you're going to do is you'll go flat pitch and allow the aircraft to just start falling. Now, as it falls, you'll incrementally pull in pitch into the rotor disc, and what it's working as doing is it's producing kind of like almost like a parachute like effect, and it starts to slow the helicopter's descent down while simultaneously creating forward lift, because as the blades spin, it also is producing lift so that way it can slide forward. Now, as this goes down and down and forward, you'll eventually just pull all your lift and it'll flare and you'll land on the ground more or less like normal if done correctly. Now, this is a pretty common thing to do. Like in order, if you're going to qualify as a helicopter pilot, you have to learn how to auto rotate, to the ground. And helicopters have been doing it for a really long time, saved a lot of lives that way. It also highlights the importance of being able to manipulate the rotor system, so that way you can keep yourself from just effectively becoming a rock above the ground. It also highlights the need for that transmission to keep spinning. So on the OH-58, you'd have a thing called a K-flex, and what that K-flex would do was allow for the transmission and the engine to be at different angles, but still be connected to one another. But in the event that something were to happen, and say that the engine were to lock up and not want the K-flex to spin, there was a freewheeling unit on the front hand side of it that whenever torque dropped off, it basically detached itself mechanically from the engine to allow the transmission to continue to spin, because that was directly tied into the rotor system. If the transmission were to lock up, the rotor system had no way to break loose of the transmission, and they would just basically stop, and you would just fall to the ground. And then your only hope is that the engineers designed it to crash really, really well, like an MD-500 does. And so, like, helicopters are probably not your best bet to have an engine failure in, but if you do, you have options through auto rotation. All right, something else that's fundamentally unique to Rotorcraft is the rotor itself. So let's talk about like blade construction and the fundamentals of aircraft blade or rotorcraft blades. So what goes into a helicopter blade? How is it made? What are the different types of constructions that we could have? How are they shaped, and how do they work? All right, this is a helicopter blade off of a Bell 407. It's composite in construction, and it's probably one of the most common types of helicopter blades that you're going to run into out there, both in its actual, the blade itself, but also the way that it is manufactured. Now, there's two types of ways that helicopter blades are generally manufactured. One is they're going to be solid metal, like a prop. You'll see that in a lot of old Soviet era, like the Mi-8 and the Hind, those types of helicopters. Most all of them now are made out of some sort of composite structure. Now, the internal workings of every single helicopter blade is going to be a little bit different. So if you think about like a Black Hawk blade, it actually has a halogen tube that goes down the leading edge to help conform its shape and reduce its weight. And then the composites are layered on top of that. So you'll have unique aspects of that. But however, be it steel or composite construction, they all have some very similar types of parts and pieces that we're going to cover real briefly, so that way you understand what we're talking about when we're talking about rotor blades. Typically, you'll have 1 to 2 bolts that will connect a rotor blade to the rotor hub itself. In this scenario, this just basically sets up against the hub, and then there's a bolt that comes right down to it, and you have a large, massive nut that goes on the bottom that's torqued and then safety with a cotter pin. Some of these blades have two holes in them, one for a permanent bolt and one for an expandable bolt, and that allows you to pivot the blade on that one bolt, so that way you can fold the blades up and then tuck it away into a hangar or wherever. Not as common on civilian aircraft, but there's a lot of ex-military aircraft floating around in the civilian world that you could come into contact with. Expandable bolts make the rotor blades very convenient to store and hangar and to ship over a long period of time. You could see those any number of places. Some blades also have devices like this to help stabilize it and give it another point of contact that, and you'll see this when we get into the different types of rotor systems here in a minute, that keeps it from hunting back and forth as it goes around. Now, in a fuller articulated rotor system, you want some of that, and so you'll see different varieties of blade construction in that regard. Some of them are meant to not go anywhere, and some of them are meant to go somewhere to a certain amount, so that way that blade can move and be as efficient as possible. And for the most part, the blade is fairly uniform all the way through, for the most part. There's going to be a honeycomb core that's on the inside that helps give it shape with carbon fiber or fiberglass or something that's overlaid on top of that and then set up. So that way, whenever you go to do repairs, think carbon or fiberglass repairs as opposed to metal repairs. Now, it can be deceptive because there is a metal tip right here that goes over the leading edge. That's called an erosion strip. The erosion strip will go from here almost all the way down to the length of the blade. Now, when I was in the Army, one of the things that we used to do every day was we would spray paint this black, and that provided a sacrificial layer for to come off the blade, so that way it didn't wear prematurely on the erosion strip, and it made the blade look a lot more well kept. And so that's something to keep in mind. The erosion strip is attached with these series of screws that will go down the length of the blade, and then overlaid with a substance that gets then ground down so it's nice and uniform and it's nice and flat. On the tip, you'll have a cap, and this cap has a tie down point on it. Now, typically what will end up happening is you'll have a clip that goes to that, and it'll come off to a rope that you tie off to the skids, and that keeps the blades from flapping and putting excess wear on the rotor disc, and also keeps it from spinning in the wind, which could cause a number of problems on top of being unsafe to walk by. The blade itself is made with usually a kind of a neutral camber. It's not necessarily like bulged out on one side or the other, and it goes through the air like this, just like a regular wing, or if you think of like a kind of a cross section on the B-2 bomber, that you have that kind of like nice wing type of shape. That allows it to produce lift no matter which angle or pitch that it's at, and it's fairly uniform production of it, because as the rotor blade goes around, it changes its pitch based on how the controls are set. Now, this device here is a trim tab, much like a trim tab inside of your on your wing on your aircraft, except for it's set manually by the mechanic off the aircraft whenever the aircraft isn't running. This will help the blade track more true. So if you have a blade that's just running high for whatever reason, say that there's maybe an imbalance somewhere in the construction of it, you could bend the trim tab up with a trim tab bender, and it will actually cause the blade to sink back down and to be back in track. And we'll talk about track and balance here in just a little bit. Or you can go the other way and cause it to come back up. Either way, however you make the adjustment, this is a trim tab. Now, just like a wing, it has a trailing edge. And so my experience is that like a lot of your damage that you'll end up happening, or the delamination of a carbon fiber rotor blade just like this, will happen towards this end for whatever reason. There's metal in there, but there's also carbon fiber that's laid over the top, or some sort of a fiberglass laid over the top of it. You'll start to see that delamination start to happen. It'll bubble up, and what you can do is fill it with glue, and the maintenance manual will lay out all the different types of repairs that you can do to the back end of the rotor blade. Now, that's kind of like a rotor blades in a nutshell. Every one of them is different. So if you're working on a S76 or an MD500 or a Bell 206 or a Hiller, they're all going to be totally different based on that in particular aircraft. Because you think that that in particular aircraft has its own power plant, transmission, and set rotor speed for the aircraft to operate in. So in order to set the rotor speed correctly, you have to also have the right blade weight, and they'll have a range in which the blades can weigh as you kind of like balance them out. Now the TCDS will tell you who the manufacturer of the blades are and like what blades are authorized to go on there. Don't deviate from that. Don't go and start trying to play around with this sort of thing, because even if you get it to work and you make it work, you could put too much stress on the transmission primarily or the engine, and next thing you know, you have a crashed helicopter. Helicopters want to crash. They're very easy to crash if you don't maintain them and operate them appropriately. So don't take any chances when you're working on something like this. There's just too much going on for you to deviate too far from the engineering. Now, believe it or not, there's actually several different types of rotor systems that are out there. There's a rigid rotor system, a semi-rigid rotor system, a fully articulated rotor system, on and on. And so let's go over every single one of those and talk about how is one rotor system different than the next? What makes them work?
All right, so the three main types of rotor systems: the semi-rigid, the rigid, and the fully articulated rotor system. Now, this is a semi-rigid rotor system. They typically are composed of two blades, and they're rigidly mounted to the main rotor hub. The main rotor hub is free to tilt with respect to the main rotor shaft on what is known as the teetering or a flapping hinge. It allows the blades to flap together as a unit, and as one blade flaps up, the other one comes down. And since there's no vertical drag hinge or lead lag forces that are absorbed and mitigated by the blade bending, which makes it for a little bit of a rougher ride. The semi-rigid rotor is capable of feathering, which means that the pitch angle of the blade changes. And it's made possible by the feathering hinge that you can see on there. So basically, a semi-rigid rotor system is going to allow it to teeter one way or the other. It's going to allow it to feather, but it's effectively any vibration is going to be dampened by the bending of the blade, making it for a rough ride. All right, the next type is the rigid rotor system. They are mechanically fairly simple, but they're structurally complex because the operating loads has to be absorbed in bending rather than through different hinges. In this system, the blade roots are rigidly attached to the rotor hub, and the rigid rotor system tends to behave like a fully articulated system through aerodynamics, but without any of the flapping or leading lag hinges. So instead, the blades accommodate these motions by bending, and they cannot flap or lead or lag, but they can feather, so they'll pitch up and down as they go around. As advancements in helicopter aerodynamics and materials continue to improve, rigid rotor systems may become more and more common because the system is fundamentally easier to design, but it offers both the best properties of both a semi-rigid and a fully articulated rotor system. So it's very responsive, and it's usually not susceptible to mass bumping like the semi-rigid systems. You get a little bit smoother ride on it, and you can definitely tell this if you fly on, like I say, a Black Hawk versus like an old like a Bell 47 or something. Way different experiences. The rotor and the fuselage move together as one entity and eliminates much of the oscillation that's present with other rotor systems. Other advantages of the rigid rotor system include a reduction in weight and drag of the rotor hub and a larger flapping arm, with significantly reduces control inputs. It's easier to fly and operate. Without the complex hinges, the rotor system becomes much more reliable and easier to maintain than the other rotor configurations. A disadvantage of the system is that the quality of the ride in turbulent or gusty air. So it wants to, if you get into kind of choppy air, you're really going to feel it with this rotor system, because there are no hinges to help absorb the larger loads. Vibrations are felt in the cabin much more than other rotor head designs if the weather kind of goes south on you. All right, the next one is the fully articulated rotor system. But let's break that down. We're going to talk about like how does it allow the blades to articulate. So first off, it allows the blade to lead or lag. It means it allows it to go back and forth as it comes around. So that blade might get compressed as it comes around and starts getting a lot of air pressure on it. It allows it to come backwards as it comes, back on the descending side of the rotor hub. It might extend out and be able to come a little bit further forward relative to the rotor hub. This is provided by the lead lag hinge, allowing the blade to pivot. Now you can accomplish this through a variety of ways, and one that we're going to talk about here a lot because our example uses them is with the electrometric bearings. There's several electrometric bearings built into the OH58D's hub that we're going to look at, and this will allow for some of the lead lag and change in blade position. But that's the first way it articulates, is by leading and lagging. Now, flapping also allows the blade, the whole main rotor disc, to pitch one way up or down. This allows the controls to actually be a lot more effective because you're allowing the rotor disc to tip one way way over, one way way high. It also helps enable safety on the ground because as people approach the aircraft, the pilot can simply just like lean the rotor disc the other way, and you have a lot of head clearance on there. Now, the backside of that is that also if they come, if they tip towards people, you can put those blades really close to the ground and making it extremely dangerous for anybody to approach. But that's a flapping hinge. Now, a good example of a fully articulated rotor system was the Kyle Warrior. It's basically a hopped up Bell 206, and because of the ability to let those blades move independently of each other, it provided a very, very nimble, very, very efficient platform to work with. Now, what enabled the Kiowa to be able to do that was now, all an elastometric bearing effectively is going to be a rubberized polymer with metal rings that go around it, making this like sandwich-like feature that allows for like 360-degree motion in every single direction while maintaining its structural integrity. Now, on the 58, there's elastometric bearings on the hub and all over the place, and they've become very, very common throughout all of aviation. You can see this looks like a Blackhawk's tail where they've been in place in there. The main thing you want to look for these things is that you can't tolerate any delamination. If they start to come apart, they've got to go because they have so much force and so much just there's so much going on there that if they start to come apart, you're not going to get a whole lot of warning before they just like completely disintegrate and have a catastrophic failure. So have a high standard whenever you're dealing with elastometric bearings. But they are what enable a fully articulated rotor system to operate the way that it does. I don't think in terms of these rotor systems as being superior one to the other. It really kind of becomes the right tool for the right job. So an articulated rotor system, you have like really good control response. It's very nimble. It's super smooth and stable, but it's more complex and it costs a lot of money. And it also costs a lot of money just to maintain. Like I said, like with the 58, there was a high degree of attention and care that went to those elastometric bearings as well as other parts of the rotor system. Now, we were able to do a lot with the helicopter, but it does come with a heightened maintenance load on it. A semi-rigid, such as the teetering or underslug or a seesaw, they're simple and easy to hangar due to just two blades. It means that they are easy to deal with, but their reaction to control input is not as quick and is articulated on an articulated head. Vibration can be higher than multi-bladed articulated systems. So they're simple, they're cheaper to operate, they're cheaper and easier to hangar. And so if you think about like people that are operating in environments where maneuverability isn't necessarily key. So think about like doing crop duster work or maybe survey over pipelines, or where you're just basically flying. For the most part, kind of straight level flight with occasional turns here or there, then you're going to find that semi-rigid, especially if you want to keep the cost down and the aircraft availability super high. Whereas articulated with like the 58, we were doing military operations. It requires a lot of maneuverability close to the ground, and we need to have the aircraft to be up, so you had 10 guys working on this one little helicopter to keep it going. Whereas, okay, so the rigid system, however, simple design, crisp response. It's kind of like the middle ground between the semi-rigid and the articulated, but they have higher vibration than the articulated rotor in like rough air and things like that. So they all have their advantages and disadvantages, and it really just kind of comes down to what's the mission of that aircraft. And you'll find that's pretty ubiquitous with any sort of aircraft design or purchase or whatever. You're asking yourself, what am I going to do with this aircraft? How many people am I going to have to move? What kind of weight am I going to have to move? What's my budget both in time and in dollars for maintenance and downtime? No different than selecting a rotor system.
All right. The other big thing that makes a helicopter just totally different than everything else is the transmission. Now, this is the one no-fail component. If the transmission locks up, there are ways to keep the aircraft flying, or not really flying, but like at least to let it auto-rotate to the ground. But the transmission is kind of like the heart and soul of the helicopter. It's going to take power from the engine. It's going to transform it into a usable RPM in the rotor, and it's really kind of your everything. So let's talk about helicopter transmissions.
All right, so let's orient ourselves to where the transmission's at on a helicopter. If you look at this graphic, you'll see there's a little shaft that comes down that says to the engine. So imagine the engine sitting right there. Now, as the engine turns, it's actually going to turn the gearbox as well. As it turns the gearbox, it's going to step the RPMs from the engine down to a usable RPM that then gets output on the engine. That is going to get fed directly into the main rotor transmission. And from the main rotor transmission, at least on this model, it can be different depending on which helicopter. The main rotor transmission is going to take, say, 2,700 RPM and scale it down into like 450 RPM. Now, it does that by taking the input drive and spinning a ring, and then taking planetary gears and scaling that outer ring RPM down to a usable RPM for the rotor itself. The main thing is that the rotor cannot spin as fast as the engine can spin, simply because the rotor is heavy and it's large, and so you have to be able to make the two kind of meet in the middle, so that way you maximize the engine output as much as you possibly can to get as much power as you possibly can to the rotor without over torquing the engine. And speaking of torque, let's kind of go over what torque looks like in a helicopter, because you're going to hear that a lot in dealing with these aircraft. Okay, torque is always going to be denoted by the letter N. So, just like whenever you fly an aircraft, you have your different V speeds, and V is the fancy way to simply say speed. So, like VY is your best glide speed. So it's the speed for best glide is denoted by the letter Y is such and such. So VY, and in the realm of helicopters, in the realm of turbine engines, period, N is always going to basically denote RPMs, or the level of torque that gets end up placed on something. So if you look at the bottom right hand corner of this graphic, you have NR and NP. NR means the torque on the rotor, or the RPM, percentage of RPMs, max RPMs on the rotor, and then NP means the max RPM for the engine itself. So in theory, if you have both of them in the green, you have max available power coming from the engine that is at the optimal level that the transmission and the rotor hub can convert that power into flyable lift for the helicopter. If one of them gets off, let's just run through a couple of scenarios. Let's say you have low rotor RPM. That means that the aircraft is effectively going to fall, because it's not producing enough lift to stay aloft anymore. So that's very clearly a problem. However, if let's say you get your NR too high, that means that you're running a risk of overheating the transmission, stripping out any number of gears along the way, and causing it to either seize, the rotor hub to literally depart the aircraft totally, any number of things that are very, very bad for the helicopter. It means you're on a risk to crash. So you definitely don't want, you want to keep your rotor RPM stable. Now, this becomes a challenge as you start to pull pitch, because if you think about it, as that rotor is spinning, and the blades start to grab more and more air, it becomes harder and harder and harder on the engine to maintain that NR exactly where it needs to be. This is why whenever helicopter pilots, when they first started flying helicopters, they would do the broomstick drill. They would basically sit in a chair and they would imagine pulling the collective up to pull more pitch in the rotor, and they would roll their wrist so they would give it more gas as it comes up, and they would make that like muscle memory. So that way it came up and went down, rolling the throttle on and off. And we'll even demonstrate that in class because it's a little bit more difficult to do it on a video. But that's why nowadays FADEC, which you guys haven't encountered yet, but it's the full authority digital engine control, basically says like, hey, look, we're running up on NR. We need to throw more gas onto the engine so that way we can maintain the correct rotor RPM. Simultaneously, if it went too high, then they would want to pull engine power back, and so whenever you drop the collective, you would also roll power off to bring that NG down to keep the NP from getting too high as well. And so there was a constant effort going up and down, up and down, up and down, pitching the blades one way or the other way, and having to make engine adjustments as well. It gets into how flying a helicopter can be kind of complicated, because as you're doing this, you're also changing the torque effect on the helicopter as it ascends and descends one way or the other. And so that being the case, you have to also add in more pedal. As you add in more pedal, you put more demand on the rotor, which puts you back at square one. So you end up going in this crazy circle, and that's what made helicopter flying very, very difficult. And if you ever notice a helicopter pilot, he's always making little adjustments, and this is why he's kind of like always chasing this circle that will never get to the end of it all. Then simultaneously, let's look at the RPMs for your engine. So your NG, or in this case NP, as the engine gets under power, you're simply just leaving power on the playing field. Like you could be using more power and having a low engine RPM. That's not really going to be good. However, it is way better than running too high of an engine RPM, because if the engine gets running too fast, it's going to get too hot. You run the chance of something seizing, flying apart, just like with the transmission. So you definitely don't want to do that. Now you have these situations where, let's say you're in a descent. If you don't roll power off and you let the rotors get going too fast, you could overspeed the engine. You could have an engine failure, if not an entire drivetrain failure. And so you can see how these two are linked together, and you're always watching. It doesn't matter what helicopter you're flying, you're always watching your rotor RPM, your engine RPM, constantly, like with one or the other. And there's a bunch of different ways to monitor these simultaneously, and that's what this graphic is showing you. There's all these different dials that's basically telling you the same information. Here's where your rotor's at. Here's where your engine's at. You could have those sliders on either side that go up and down. You could have a digital display that just gives you two numbers, and you know kind of like where you're at. You could have a circular display that you're trying to keep both needles in the green and then make the adjustments as necessary, and that's how you ingest that information. But just remember, rotor RPM, engine RPM is basically everything when it comes to flying a helicopter or operating a helicopter, and this will become part of your maintenance callouts as well, because they'll say like at such and such of rotor RPM. Say like I remember we always had a 1-to-1 hop at 32% NP on the 58. For whatever reason, 30 to 35, if the blades weren't balanced right, that was the torque range where you'd catch up some kind of like weird harmonic resonance that would cause the helicopter to hop really, really bad. But you could overpower it and just get through it, and it would kind of level back out. That still doesn't mean that there wasn't a problem. There was, and we had to go fix it. But that was the range of torque it seemed to manifest the worst. So that is NG and NP in the indication systems that will tell you what they're at. All right, now what happens if, let's say, the engine were to seize up? You would have to have some way to disconnect that engine, which is basically sitting still like a rock, to allow the rotor to continue to freewheel so you can auto-rotate and get to the ground. That comes in the form of a clutch, and there's several different kinds. This is a belt-driven clutch, like you would get on like a Robinson helicopter. So if you go up to like one of those like R-22s and you look on the back, you'll see a bunch of belts going. Those belts will turn, and it basically has a clutch at the bottom of it. If the engine were to lock up or stop or quit, the once you hit a certain RPM, the clutch will disengage and allow the rotor to spin. Now you still have full command of the rotors because it's linked into the flight controls to allow you to auto rotate. But what it does, it isolates the engine so that way the engine can't stop the rotor. Now, with all of these situations, there's not like a rotor clutch that it can come off. But just by nature of it, the rotor generally goes through the transmission and is hard, wired into it. So if the transmission locks up, you end up losing your rotor. That's why it's really, really important to respond to any sort of like services, chip detection, anything like that inside of the transmission, because if the transmission goes, we all go. And so you absolutely have to take care of it. But that's a belt-driven clutch. All right, this is a centrifugal style clutch off of a Bell 47. What happens with these is that like there are springs that have little teeth that grab a outer race as the helicopter spins up. And once you get to a certain level of RPM, those teeth will start to flail out, and as they flail out, they grab the outer race and they actually start to spin the rotor at certain RPMs. Now, if all of a sudden those RPMs were to go away and just quit, so the engine would seize, those teeth would collapse back on and allow the rotor just to spin. It'd be a very terrifying situation, but it would work and it would keep you alive. So those are your two types of clutches that you could potentially come across. Now, another type of, you could call it a clutch, even though it's not technically a clutch, is a freewheeling unit. Now, a freewheeling unit works very similar to a centrifugal clutch, that like at certain RPMs, the little teeth engage, causing the main rotor to turn, but once you fall below that RPM range, it disengages, allowing the main rotor just to spin freely. And so this is probably your most common type of clutch device that you're going to see on turbine helicopters. You'll see the other ones. You'll definitely see the R-22s have the little belt-driven clutch, and some of the older helicopters have centrifugal clutches. But by far, anything that's driven by turbine is probably going to have a freewheeling unit, and I'd be interested to run across any of them that don't. The one thing that's unique about helicopters is that most airplanes they have the same kind of construction. Helicopters, though, you'll see guys that specialize in certain models of helicopters, because that model of helicopter is going to be fundamentally unique to other models of helicopters, and that's just kind of the nature of rotorcraft. And because they're unique in just their design, and they're unique in their purpose. Like what you could use for a flight trainer in an R-22 is going to be cheaper. It's going to be a lot more forgiving, a lot slower for your student. You don't want to turn them loose on, say, like a MD-500 Notar, because it's way more power, way too nimble. There's all kinds of bad things could potentially happen. Simultaneously, that Notar is not going to be the ideal situation for, say, like doing long line work, even though they do use them for that. You might want, say, like an old, like a Bell 412 or something that has a lot more capability to lift things than other ones. And those different little design differences will dictate how the inner workings of that particular helicopter, kind of come together.
All right, lastly, helicopters, by the virtue of being able to level land like that, sometimes will have skids. You won't see skids on aircraft unless you have a helicopter that has, or an airplane that has skis, and that's kind of similar, but not quite the same thing, and it's only used in like really icy conditions. So let's talk about like skid shoes, and what does a skid shoe inspection look like? We talked a little bit about it in landing gear. Let's talk about a little bit more here to make sure that we understand what a skid shoe is.
Okay, so a skid shoe is nothing more than a sacrificial layer of metal that goes underneath the skid of a helicopter. Here's the thing: is that like in order to keep directional control in the event of a tail rotor failure, helicopters have to have forward airspeed, because what you'll notice is that most all helicopters have a vertical stabilizer component on the back of the empennage. As they fly, that air comes over that stabilizer and helps keep the helicopter straight without making a lot of tail rotor inputs. Now, let's say you were to lose your engine and you're going to fly forward. You need to keep that forward airspeed coming to, or you lose your tail rotor and you're going to fly forward. You're going to need that airflow to come over that stabilizer to keep the nose pointed in a right direction without really having to make a lot of high torque corrections, because the more you torque the main rotor, the more that tail rotor is going to, or that tail is going to want to kick around because of action reaction. So they set it up so that way they can do what's called a run-on landing. So you have a skidded aircraft, or even a wheeled aircraft for that matter, and instead of coming landing straight down in controlled flight, since you don't have your tail rotor, you're going to come and land like an airplane. You're going to land on a runway and just roll out. Well, if you don't have wheels, like say a Black Hawk or an Apache or Chinook or an S-76 or whatever, say you're in a Bell 412 or an OH-58 or a Bell 206, and you just have skids, you're going to land. And what you don't want to do is rip the landing gear off, or drag holes in it or anything else like that. So you want to have something that you can sacrifice to maintain the integrity of those skid shoes. So whenever you land, or of the skids, you're going to land, it's going to skid across the ground, and it's going to eat up those skid shoes rather than the landing gear tube itself. And that is what a skid shoe is. So you're going to end up having to inspect those. A lot of times the clamps on the side of them will break over time just from just flexing, and they'll rust and all kinds of good stuff. And then if they ever do any landings, you're going to have to jack the aircraft, change those skid shoes out, so that way you have it for next time. But yeah, real simple. That's all that they really are. It's a pretty simple part and component to contend with. But yeah, so that's it for your rotorcraft fundamentals.